Hey everyone, in this video let us talk about crystal field splitting in tetrahedral complexes. See, here in tetrahedral complexes the crystal field splitting is very much different. It is just exactly opposite to that of octahedral complexes. I mean, the way the orbitals will get split is exactly opposite to octahedral complexes. So here what actually happens is, see, a tetrahedral complex where the coordination number is 4, that means if you have 4 monodentate ligands, so let's see what happens. Okay, so 4 monodentate ligands. Suppose if this is your central metal atom, central metal ion, okay, whatever it can be, and you have the 5 d orbitals here. So one is like dxy, dyz, dzx, right? So these 3 orbitals will exactly lie in between the axis, whereas the orbitals dx square minus y square and dz square will lie along the axis. And initially, just before approaching any ligands, all the orbitals had equal energy. Suppose if this is the increasing order of energy, so all d orbitals have got same energy. Okay, so the 5 degenerate d orbitals we say. When the ligands starts approaching, so still when they are far away, all of a sudden all the orbitals energy increases slightly, so little higher I'm going to place the orbitals. And now as the ligands approaches closely, okay, see, they approach in a direction where the dxy, dyz and dzx are there. Okay, so look at here, I have shown 2 ligands, here I have shown 2 ligands, altogether 4, because we are discussing the case where we have 4 monodentate ligands. Okay, so see the direction of their approach, it is exactly opposite to the direction of dxy, dyz and dzx. So obviously what we can conclude is these orbitals will experience more repulsion. As a result of that, they will have more energy, and the remaining 2 orbitals which lie along the axis experiences less energy, and as a result they will have lower energy. So this is how, due to this energy difference, they are getting split up into 2 sets here also. Okay, so the first set, the set which has higher energy is our T2G set now, dxy, dyz and dzx. I'll write these names above, okay, so that it is more convenient, dyz and dzx. And the set which have lower energy is dx square minus y square and dz square. This set is named as EG set. Okay, so just exactly opposite to that of octahedral complex. In case of octahedral complex, what I have shown, this we have put it down and this we have placed above, right? So now the thing is opposite, and this energy difference between T2G and EG set is called as CFSE of tetrahedral complexes, which is denoted as delta T. T represents tetrahedral complexes. Okay, and you know what? Delta T is much lesser than delta O, guys. Okay, so you don't have a much larger energy difference, you'll have a very small energy difference irrespective of the type of ligand. Ligands can be a strong field ligand or ligand can be a weak field ligand. No matter what type of ligand you have, the CFSE, the energy difference between T2G and EG is always very less. Okay, so you have this relationship between delta T and delta naught, guys. So delta T is equal to 4/9th part of delta naught. So this is one of the important relationship. Okay, so delta T is very lesser. So we can conclude that all tetrahedral complexes are high spin complexes. Tetrahedral complexes are high spin. Okay, low spin complexes are rarely observed. Okay, so they all are high spin. That means whenever you start filling up electron, say suppose for D3 configuration. Okay, see, first electron you will place it here because these guys are the orbitals which have lower energy. Second electron here. Third electron, instead of pairing here, it will always go up, guys, because this, you know, here pairing energy is much greater than delta T. Delta T is very small, right? Very less energy gap is there. So the third electron, instead of pairing, it will go up even if you have a strong ligand here. Okay, so even if complex has a strong ligand, third electron would likes to go up instead of pairing here. Okay, so that's the reason we say all tetrahedral complexes are high spin only. Okay, and the way of writing electronic configuration is just similar to the octahedral complexes. Say suppose if somebody asks you, write the electronic configuration of NiCN4 minus 2. Okay, so here let me write the electronic configuration. See, look at here, nickel, its atomic number is 28. Its ground state electronic configuration, outermost electronic configuration is 3D8 4s2, isn't it? So now here nickel has its oxidation state +2, so its electronic configuration is 3D8, right? 3D8 in the sense it is a D8 system, so this complex has 8 electrons. So let's arrange. Okay, so this is a EG set which has got lower energy, this is a T2G set which has got higher energy. So let's arrange the electron. First electron, second electron, third electron will go here instead of pairing up. Though you have a strong ligand, you know, instead of pairing here, third electron is going up, fourth electron, fifth electron, sixth electron, seventh electron, eighth electron. So the electronic configuration is EG4 T2G. How many electrons? 1 2 3 4, right? TEG4 T2G4 is the electronic configuration of this complex. Okay, so just the orbitals are flipped up. Okay, that's it. That is the only difference. The way of writing electronic configuration and everything remains same. So only thing is, remember that though you have a strong ligand, you know, since pairing energy is much greater than delta T, the complexes you will always get is high spin. Low spin complexes are rarely observed. Okay, so most of the time the complexes are high spin only. Fine. And now one more thing is, say this is a barycenter, right? See, the energy of T2G set will increase to the extent 2/5 of delta T, and the energy of these guys will decrease by -3/5 of delta T. -3/5 in the sense what you can write, -0.6 delta T, and here plus 0.4 delta T. Okay, so this much extent the energy of these guys have been increased compared to our original energy, and to this much extent energy of these guys, I mean these orbitals, have been decreased. Minus means decrease in energy, plus means increase in energy. Okay, and don't forget this relationship. See, question can be asked this way. I mean, in one of your exemplar question, so you have this particular question where a particular complex X, okay, so which has got delta naught is equal to 36,000 centimeter inverse, and how much is delta T they have asked. See, delta naught they gave you, delta T they are asking. That means CFSE in octahedral complex is this much. For the same element, you know, CFSE in tetrahedral complex is how much. So just use this relationship. So delta T is equal to 4 by 9 into delta naught. They have given no how much? 36,000. 9 fours are right, 4,000 here. That means 4 fours are 16. That is 16,000 centimeter is your answer. Okay. So you have a particular complex X. If it is there in a octahedral form, it had a CFSE of this much. The same complex, if it was in a tetrahedral form, the CFSE was this much. See, look at the difference. CFSE in tetrahedral complex is much lesser than the CFSE in octahedral complex, right? So this is how you can calculate using this relationship. So they either give you delta O, they'll ask you to calculate delta T, or they'll give you delta T, or they'll ask you to calculate delta O. Okay, so this is how you can use the relationship. And now one more information I'll give you. See, this is much the deeper aspect I am telling you, so which may not be frequently asked for your NEET examination, but you can concentrate this aspect if you are preparing JEE examination. Okay, so you have a formula to calculate CFSE. Formula to calculate CFSE. Okay, first, since we have just now discussed CFSE in tetrahedral complex, I'll give you formula to calculate CFSE of tetrahedral complexes only. Okay, so this is very simple, guys. So CFSE in tetrahedral complex can be calculated by, see, look at here, minus 0.6 delta T, okay, into number of electrons in which set it is? EG. Number of electrons in EG set, okay, plus 0.4 delta naught, okay, into number of electrons in T2G set. So this is the formula by which you can calculate delta T of any complex, guys. So look at here, this number into number of electrons in the EG set plus this number into number of electrons in the T2G set. One example I will show you. Like previously, I have written the electronic configuration of NiCN4 minus 2, right? So its electronic configuration, I wrote it as, see, 8 electrons, it's here only. So let me write its electronic configuration. EG4, T2G 4 I have written. Okay. So now you apply the formula. If you want to calculate delta T of any tetrahedral complex, first you need to write the electronic configuration, then use the formula, guys. See here, minus 0.6 into how many electrons are there in EG? 4. So once you write the electronic configuration only, you will come to know how many electrons are there in EG and T2G, no? So that is the purpose of writing electronic configuration. So this number minus 0.6, because the energy of this set is decreased by this much, no? So this number, don't forget to take minus sign, you have to take. So minus 0.6 into 4 plus 0.4 into number of electrons in T2G set. How many are there? 4. Okay. So this is how you have to calculate. So it is minus 2.4 plus 4 4s are 16, right? That means 1.6, right? So if you do minus 2.4 plus 1.6, you will get your answer as minus 0.8 delta T. Okay. So this is your answer, guys. So this is the formula to calculate delta T. So very simple actually, right? Similarly, you have a formula to calculate CFSE of octahedral complex also. Okay, so the formula is very simple. CFSE at octahedral complex, you know, you will have, do you remember CFSE of octahedral complex in the lower set was T2G, higher set was EG, right? And energy of these guys were increased by 3 by 5 of delta 0. Energy of these guys were decreased by 2 by 5 of delta naught. So 2 by 5 in the sense it is 0.4 minus 0.4 delta naught, and here it is 0.6 delta naught. So let us frame the formula now. This number, that is minus 0.4 into number of electrons in T2G set. Here came EG set, right? Because EG was having lower energy. Now it comes T2G. Whenever T2G is there, this number, right? So plus 0.6 into number of electrons in EG set. Okay, so this is the formula, guys. Okay, so using these formulas you can calculate the CFSEs, okay, in the unit delta naught. And to calculate delta T or delta naught, you must compulsorily write the electronic configuration of a complex. So writing electronic configuration is very, very critical here. Okay, so that's all about crystal field splitting in both tetrahedral complexes and octahedral complexes. And now we will discuss few questions which are there in our NCERT textbook relating to this concept, so that you will have an idea. See guys, the questions in your NCERT exercise relating to CFT is very, very simple, direct. So actually for NEET point of view or board exam point of view, only the basic idea of CFT is more than enough. You should know how to draw that energy level diagram, I mean the splitting diagram for octahedral complexes and tetrahedral complexes properly. So that is what important for boards as well as for NEET examination. Okay, so writing electronic configuration and calculating CFSE is much advanced versions of a topic. Okay, fine. So anyway, first let us discuss these questions. Exercise 9.16, it's a direct question. So draw figure to show the splitting of d orbitals in an octahedral crystal field. You have to neatly draw the figure, guys. So you have to say this is the increasing order of energy. First you have like degenerate. You can show it lines or you can show the boxes. That's your wish. And as the ligands approach, all of a sudden all the 5 orbitals energy increases. When they approach very closer, and you know the splitting takes place in this way, this is EG set and this is T2G set, you have to nicely label, and the energy of these guys will increase by 3 by 5 of delta naught, and the energy of these guys will decrease by minus 2 by 5 of delta naught. Okay, so all of that neatly you have to draw it and show. This question can appear for boards. Next, 9.17. What is spectrochemical series? Explain the difference between a weak field ligand and a strong field ligand. Spectrochemical series definition is given in a handwritten notes. It's very simple. The ligands are arranged in the increasing order of their field strength is called spectrochemical series. And on what basis they are categorized as weak and strong? On the basis of splitting capacity. Okay, strong ligands split the orbitals this way, you know, it will cause very high CFSE. Okay, weak ligands cause less splitting, it causes less CFSE. Okay, strong ligands leads to high CFSE splitting, and weak ligands always cause less CFSE. Okay, so based on the extent of splitting, ligands are actually classified into strong and weak. Fine. Now coming to question number 9.18, guys. What is crystal field splitting energy? That means they are asking you the definition of CFSE. Okay, so the energy difference between T2G and EG set is called as CFSE. How does the magnitude of delta naught decide the actual configuration of d orbitals in the coordination entity? Okay, see, if you have high CFSE, it leads to the formation of low spin complexes. Low spin configuration you will observe. Okay, so when you have high CFSE, low spin configuration is observed. When you have less CFSE, high spin configuration. Okay, high spin configuration is observed. Okay, so I mean whenever you have a fourth electron here, instead of pairing, electron would like to go to EG set. Okay, so because here pairing energy is much greater than delta naught. So here delta naught is much greater than pairing energy. Okay, so that's why instead of the fourth electron going up, the electrons would like to pair up, but here the fourth electron would like to go up, isn't it? So this is how the electronic configuration writing always depends on the extent of CFSE. Okay, so high delta naught, low spin configuration, less delta naught, high spin configuration you will observe. Okay, so these are some simple and direct questions that you have in your NCERT textbook based on crystal field splitting. And most importantly, based on CFT, we can explain why coordination complexes are colored. So we can also decide, like when a complex absorbs a particular radiation, what color it looks like, okay, what color it gains. Everything we have to be in a position to decide, right? So about the color of coordination complexes based on CFT, I'll discuss in a next video.